word of prayer. Dear Father, we thank you for this day. Again, Lord, I thank you for these students. Pray you bless our time together. Yeah, just help us to understand group action a little bit better, Lord. In your name I pray. Amen. Okay, so last time I gave a dreadfully slow lecture. My apologies for the lethargy of Friday. Don't worry, I'll make up for it today. Let's see here. What are we? Lecture 19? We're actually still on group actions and counting. All right. Just so you know, going forward this week, I will cover the CeLo theorems probably, and I hope to say some words about finite simple groups, but those are mostly informational. All right, the meat and potatoes, if you will, whatever you want to call it. The substance of this part of the course is group actions, and the counting, and also the lattice theorem, which I hope to cover Wednesday. Okay, so here we go. So we covered what the definition of a group action was last time, right? And showed you a few of them. Here's another example just to get us started. If you have H, a subgroup of G, then you can define action of H on G according to the following rule. I could say H dot X equals to X H inverse. This is different. I defined it H times X last time. This is a different action you can define of the subgroup H on G. And it's easy enough to prove the different axioms, right? So like, of course, E times X is what? XE inverse, which is E, which is X. Okay, so there's that one. And the other thing, of course, is that AB times X, which is what? That's X times AB inverse, but Sock Shoes says that's X B inverse A inverse, which, by the way, is X, it's kind of left-handed or something. B dot X times A inverse, which then is B dot X. Oops, it takes me a while to get into the way of this thinking. A dot B dot X. So as you can see, both axioms for the group action satisfied. So it's a group action of subgroup H on G, a different one than I defined last class. What are the orbits of this one? So let's see, that would be H times X, such that H is an H, right? So what would that look like? XH inverse, right? But I would encourage you to convince yourself that's the same as saying what? X times K, such that K is an element of H, right? If you sort through the inverses in a group, it's equivalent to sorting through the elements of a group, right? This is just a reindexing of the group. And of course, you should recognize that. What's that? What did you say? Yeah, left coset, right? I mean, last time we found right coset. For this sort of backwards looking action, we get left cosets as orbits. Okay? All right. Again, just a reminder, definition, the orbit of X is G acting on X such that G is in the group, and the stabilizer is G and G such that G star X is equal to X again. So this is a subset of S. This is in fact a subgroup, as we'll prove shortly, of G. And all of this is for a group G acting on a set S. Fraley calls this, Fraley says that S is a quote-unquote G set. So it's kind of a useful terminology. But I also mentioned that Fraley calls this stabilizer the isotropy subgroup of the group action at X, of course. All right, so another example, just building off what we did last time. Remember we mentioned that if you have a vector space, in the case, n vectors, or not even that, let me just be a little bit more general. Vector space V over F, right? Scalar multiplication defines an action, right? So I can look at F, the non-zero scalars, across V, and I can map it to V again by C star V is just equal to the scalar multiplication of C times V. Right, so just use scalar multiplication. You can easily verify that forms a group action by the non-zero scalars. Okay, so what are the orbits? What's the orbit under scalar multiplication of the origin? What's the, you take a scalar multiple of the origin in linear algebra, what do you get? Or the zero vector, more generally. You get the zero vector again, right? So the orbit of the zero vector is just 0. What's the orbit of any non-zero vector? I mean, think about it. We're looking at all possible non-zero scalar multiples. What is this? Can you guys tell me geometrically what that is? Yeah, it's almost a line, right? So this is the line with direction vector V modulo what? What's the one thing we don't get in the line? It's a line through the origin, right? But there's no origin. Modulo 0, right? Modulo the origin. It's kind of fun to picture this, right? So if you picture two-dimensionally, at least that's all I can do. So you've got like the origin, right? And then you've got, I've only got so many colors, but I'll try. You know, you got these different orbits. Right? And what do you see about, I mean, the thing about the orbits, right, is they are what? They're disjoint, right? And every point is covered by an orbit, right? Scalar multiplication acts on the vector space. Everything in the vector space fits into the orbit of some vector. All right? Even the origin, it's its own orbit. It's just, you know. All right. So let's prove, one more example. I'll put this example over here. If S, we'll think of S as the group, and we'll define G star X equal to GX G inverse, all right, for all G and G and X and X. So I'm defining, X and G rather, I'm defining the action of the group on itself by conjugation, all right? Is this a group action? You can check. This is a group action. I'll leave it to you. It's actually in the notes. But what I wanted to point out is the orbit. What's the orbit in this case? The orbit of X. So that would be G, X, G inverse, such that G is in G, right? The orbit in this case is the so-called conjugacy class of X. It's the set of all points in the group, all group elements which are conjugate to a given group element X. So the orbit's a conjugacy class. And the centralizer, let's see here, the stabilizer, what's that? So G sub X is equal to what? That's G and G, such that what? Such that G, X, G inverse is equal to X again, right? This is the stabilizer. So can you rewrite that condition for the stabilizer into something a little bit more recognizable we've already worked with? I blurted it out a second ago there. Take the condition defining the stabilizer and rewrite it a little bit. What is this? This is Gx equals to Xg, right? So what are we looking at? We're looking at the set of group elements which commutes with X. What's this called? Centralizer, right? I think our notation, was it C sub A or was it C of A? I can't remember. C of A, okay, so that's the centralizer of A. Some people put a little sub G on there to emphasize centralizer of A and G, but I'll leave the G off. So the stabilizer is in fact the centralizer, and that should be of X, right? We looked at centralizers of A sometimes before. It's stuck in my head. Okay, so, and anything else I have to say here? What are the fixed subset? Remember the fixed subset? I called that S upper G. This was equal to what? G and G, such that G, X, G inverse is equal to X for all X in G. What is that? This is the fixed subset of the group action under conjugation. What is it? Did I do this last time? I can't remember. Did I do this last time? I don't think I did. Okay. No, this example. Okay. I thought about it before last class. You know, I can't remember. Sometimes like you remember a dream, you know, and you're not sure if it actually, okay. So anyway, this of course is Gx equals to Xg for all X in G. What is that? Right, this is the center of the group. All right. So that brings us to our first theorem, which I've mentioned, but I haven't done yet. I don't think I did this. Did I prove this last time? I don't believe I did. Theorem, the, you know, if S is acted on by G, then, and X is an element of S, then G sub X is a subgroup of G. All right, so proof here. Let's see, so first of all, notice that E is an element of G, right? And E star X is equal to X by definition of group action, right? So what's that say? What does that say about the identity? It stabilizes X, right? Right, it's in G of X, right? So what's that mean? Not empty, right? So we've got it's not empty. You see where I'm going? We're going to do subgroup test, right? I'll do it in 2 steps because I'm not feeling particularly clever today. Let's see here. So let A and B be in the stabilizer of X, right? and consider, so AB acting on X is equal to what? That's equal to A acting on B acting on X by the definition of the group action, right? And then I know that that's A acting on X, since B is an element of the stabilizer, right? B takes X to X. But then, of course, that's equal to X again because A is an element of the stabilizer. So hence, AB is in the stabilizer, right? I probably should have made this a homework problem. Oh well. I'm not done. All right. Sorry, I already typed it up. So also, if A is an element of the stabilizer, right? Then, of course, A is an element of the group as well. And so there exists A inverse in G such that what? A inverse is equal to E. I'm not telling you anything terribly surprising, right? So consider, oh, here, let me make sure I don't waste a bunch of our time. Follow my. So consider, we can write X, start with X. X is equal to E times X, right, under the group action. But hey, that's A inverse times A times X, because that's the identity, right? But then using the sort of associativity axiom, that's A inverse times AX times X, right? But remember, A fixes X because A is in the stabilizer. So this is A inverse acting on X, bam. So this shows that A inverse fixes X as well, because X is equal to A inverse times X. So therefore, A inverse is in G of X, and we conclude that G of X is a subgroup of G by the two-step subgroup test. Okie doke. Is good? Is good. All right. Theorem. If G is a group acting on S, suppose S is a G set, and then the orbits of X partition S. Moreover, for a finite set, we have the following. We have that the size of S is equal to the sum over I of the size of the orbits, where here one x sub I from each orbit is selected for this sum. So it's a sum over the distinct orbits, okay? So the way we're going to prove this is we're going to prove that the group action naturally defines an equivalence relation on the set on which it acts. And the equivalence relation has classes which are exactly the orbits. All right? So here's the definition of the equivalence relation. We're going to say that X and Y in S are related. So we'll denote that by X. X is similar to Y, and that's going to be true if and only if there exists G in G such that what? y is equal to g times x under the group action, right? So x and y are related only if you can move x to y under the group action. And now we just need to prove that this is a equivalence relation, right? So we got 3 things to do, right? Numero uno. Notice that x is equal to e times x, right? For e and g, so therefore x is similar to x. And that's true for arbitrary x in the set, right? Number 2, suppose that x is similar to y. Hence, there exists g and g such that y is equal to g acting on x. How do we solve that for x? Act by g inverse, right? That gives us g inverse acting on y is equal to g inverse acting on g acting on x, which by the way is x again. Using the associativity of the group action and the fact that g inverse g is the identity, and the identity acting on x is x again. So this shows then that there's a group element which when acting on y gives you x. Therefore, y is related to x. We've done this for arbitrary x and y in the set, so we've shown that the equivalence relation is symmetric. 3. You're like, you should have made this a homework problem. Yeah, probably. Suppose x is equivalent to y and y is equivalent to z. That implies that there exists an h and a g in g such that y is equal to h times x and z is equal to g times y. So check it out. Z equals g times y, but that's equal to g times h times x, which is equal to gh times x. Therefore, x is related to z. Transitive. So we have an equivalence relation on the set by the group action, and the equivalence classes, right? What's the equivalence class here? The orbit of x is equal to what? It's equal to g times x, such that g is in g, right? That is exactly the equivalence class. That's exactly the equivalence class of this equivalence relation I've just shown you, right? What does it mean for x and y to be similar? It means that there's some g such that g times x is equal to y. So that's exactly the set of elements of S which are similar to x. The equivalence classes of this equivalence relation are the orbits. But we know that equivalence relations partition a set, right? So therefore, you have it. So we've shown that the orbits partition S. And then this, well, this is just counting, right? The orbits are also what? Equivalence classes are what? They're disjoint. So if you want to count the number of things in S, you just count the separate orbits one at a time and add them up. Counting gives you that this formula holds. That's it. Okie doke. Well, that brings us to our next theorem. Let's see here. So if G is a group which acts on a set S, all right, G acting on set S, then the elements of the orbit of X are in 1-to-1 correspondence with the left cosets of the stabilizer G sub X in G. Okay, so proof of this. What we need to do, right, is basically to find a mapping, which is a bijection, right? So we're going to define a function, f, that goes from the orbit of X to the set of cosets. Now this G mod Gx isn't necessarily a factor group. I'm not assuming that the stabilizer is a normal subgroup. Like, we don't know that in general. It might not be. But still, we can look at the set of cosets in general, right? And we proved that the set of cosets has some nice properties, right? So, like, for example, what's the number of cosets? We know this even when the group is not normal. The number of cosets is the order of the group divided by the order of the subgroup, right? It's part of Lagrange's theorem. Or it's a corollary, depending on how you look at it. Anyway, so this function, and what's the function? How are we going to define the function? It's a little bit sneaky. For y in the orbit of X, all right? What's that mean? That implies that y is equal to g times x for some g, right? For some g and g. And so we're going to define f of y equal to what? Well, f of y is going to be equal to g times gx. In other words, it's going to be the g coset of the stabilizer of X. Now, it's a little bit of, you're not used to seeing definitions of functions like that, right? Like, you're saying f of y, but there's no y in the formula, right? I mean, it's kind of indirect, the definition, so we have a couple things to confirm. First of all, f is clearly into, right? The assignment of y is to a coset of the stabilizer of X, right? So it's definitely in here, so that's good. Is it single valued? So how would we check single valued? Suppose we had different, suppose y and z are both elements of the orbit of X, right? The orbit of X is not a single point, it's a set of points, generally speaking. So you have different representatives of the orbit. The picture I just erased, you could take different points on the lines, right? Those would all be in the same orbit on a given line. And let's see here. So what's that mean? Means y is equal to h times x, and z is equal to what? Z is equal to g star x. I'll tell you what, I'm going to stop this and just project here. I mean, I could work it out, but I think I'm making a call here. I've got examples I want to show you. Unfortunately, I don't have those typed up, so I need to make sure I have time. Come on. Wake up. So you guys have a good weekend? Patriots won? What are Patriots? NC State lost. Yeah, I saw that. by a 33-yard football field goal or something. Yeah. I don't usually know this sort of thing, but since I've taken to following the Trump on Twitter, I noticed NC State was trending. I'm not proud of this. He's our idiot. We have to understand him. Let's see here. Come on. What the what? I dare you to defy me. Let's see here. Okay, thank you. This proof is not complicated, but it's got a lot of words. So we're trying to prove that this function is actually a bijection. So the tricky part is to show it's well defined. So if you have two different representatives of the orbit of x, y, and z, then they're both reached by action of a group element by x, all right? And they both words. Let's see here. So I'm supposing y is equal to h times x for some h and g. Of course, that means that h times x is equal to... Now, why is it equal to... Why is h times x equal to g times x? I think that's the thing I'm forgetting. I think I just have the inability to remember what... Yeah, because I have the inability to remember what I wrote 3 seconds ago. That's what's catching me up here. So yeah, g star x here, and then y is also equal to h star x. All right, so this is equal to that. If we act by h inverse on both sides, that gives us h inverse g times x is equal to x, which shows you that h inverse g fixes x, right? So that means h inverse g is in the stabilizer, which means that the h and g produce the same stabilizer coset, the same g sub x coset, which is to say that this function is single valued because the function maps to the g sub x coset. And then injectivity is easier. Once you got that out of your system, f of y equals to f of z implies that this is equal to that. But if this is equal to that, that means that h inverse g is in the stabilizer, which means that this is equal to that, which again, working backwards, means that h times x is equal to g times x, which is to say that y is equal to z, because this is y and that's z. And then surjectivity is just kind of dumb. If you have a g coset, then that means that if you look at y equal to g times x, then that will map to that, so it's surjective. And then so once we have a bijection, it's not an isomorphism, right? I mean, it's just a bijection, but bijections allow us to count. So the number of things in the orbit, which is in the domain, is equal to the number of things in the codomain, which is the set of cosets, right? But the number of left cosets of the stabilizer is exactly the index of the stabilizer in the group. And so that's the theorem, is that the size of the orbit is equal to the number of left cosets of the stabilizer, right? This is basically the orbit stabilizer theorem, which states that if you have a group acting on a set, then the order of the group is equal to the order of the orbit times the order of the stabilizer for any element in the set. This is surprisingly useful. Okay. Or in other words, the size of any orbit has to divide the order of the group, right? Likewise for this, I mean, the stabilizer is a subgroup, so you know that the order of the stabilizer is the order of a subgroup, so it has to divide the order of the group. That's not surprising. We know that already, Lagrange's theorem. But the fact that the size of the orbits has to divide the order of the group, that's a little bit surprising. And that's all I got typed. Sorry. But I have examples. Let's see here. Man, I really wish I had this one typed up. Oh well. It takes me about 2 minutes to write this silly thing up. and there's really not much to it. Just a lot of writing. So if you look at the set of vertices of a square, so I'm going to have to draw, I'm drawing 8 squares here. These are supposed to be squares. 0, 1, 2, 3, 3, 0, 1, 2, 3, 0, 1, 2, 3, 0, 1, 2. Yeah. Then downstairs, 0, 3, 1, 2, 2, 1, 3, 0, 1, 0, 2, 3, 3, 2, 0, 1. So what I'm trying to illustrate here is the dihedral group acting on the vertices of a square. So the set here, S, is equal to V0, V1, V2, V3, which for the sake of brevity I've labeled 0, 1, 2, 3. These are the vertices of the square. How does the dihedral group act on these vertices? Right? I've illustrated it up here. This is 1, right? This is the 90-degree rotation. This is the 180-degree rotation. This is the 270-degree rotation. So this is the sort of, we start from here. It goes to itself. That's the identity. This one is what? This is this diagonal flip, right? This one is this diagonal flip. These are, the second row is reflections. This is across that bisector, right? This is the horizontal, the vertical flip. I don't know what this is called, I forget. But anyway, these are reflections across these lines. Okay. The point is, we can do some things. First of all, what's the orbit of the 0th vertice? What's the orbit of V0? In other words, if you think about the dihedral group acting on the 0th vertex, where does it go to as you cycle over the whole group? It goes everywhere, right? Like 0 goes here, it goes here, it goes here, it goes everywhere. So this, in fact, is just equal to S again. If there exists some element in the set which the orbit under the group is the whole set again, the group is said to be transitive. So this shows that D4 acts transitively. On the set of vertices of the square. Yeah, just one. What's the stabilizer of the 0th vertex? I'll use cycle notation. I mean, this one, right? Obviously that fixes the 0th vertex. What else stabilizes the 0? What else keeps 0 at 0? Not this one, 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 not this one. Oh, that one. So yeah, this one, which we can denote in cycle notation as 1 goes to 3. And you see 0 and 2, they stay fixed. So in cycle notation, that's what the stabilizer looks like here. So you can see the orbit stabilizer theorem at work here. What's the so the orbit is what? How big is the orbit? 4. How big is the stabilizer? 2. 2 times 4 is 8. And what's the order of the dihedral group? You know, your G is equal to, I should write that. I'm an idiot. D4, right? So what's the order? I mean, that's an 8 element group. So there you go. An example. of the orbit stabilizer theorem. Although I don't think that's especially, everybody gives this example, all the books give this example. It's not especially enlightening, I don't think. Finally, returning to an old discussion in here by now. I'll start us out with this example. Suppose we look at S equal to n sub 6, which is my notation for 1, 2, 3, 4, 5, 6. I'd say, well, I guess for some people it's counting numbers. But I guess everybody's got 6 fingers, but whatever. Well, not everybody, but some of us. Oh, I'm sorry, this lecture just took a dark turn. Let's see here, 1, 2, 3, 4, 5, 6 is a set. And let's look at sigma, a permutation, equal to 1, 2, 3, 5, 6. We can look at the subgroup, cyclic subgroup generated by sigma, right? In other words, sigma to the power k, such that k is an integer, right? This is a particular subgroup of what? Of the symmetric group on 6 symbols, right? The cyclic subgroup, particular cyclic subgroup, and we can let this be G. And how would G act on? How could we let G? Well, I showed you last class. We can let a subgroup of a group of permutations act on the numbers, right? I think I gave a more general construct than that, but anyway, it acts naturally on the set 1, 2, 3, 4, 5, 6. And let's see here. You guys can tell me what's the orbit of 1, what's the orbit of 5, what's the orbit of 4. Ow. Where does sigma move 1 to? It moves it to 2. If you square it, it moves it to 3. Then 3 goes back to 1 again. The orbit of 1 is 1, 2, 3. The orbit of 5 is 5 and 6. The orbit of 4 is just 4. Right. And if you look at this, the sum of the orbits, the sizes of the orbits, right? Is what? It's 3 plus 2 plus 1, which is 6. Right? Not an accident, of course, it's because the orbits partition S. Now, here's the big brother to that example. If you look at S equal to n sub n, right, and you let sigma be a particular permutation in the symmetric group of order n, and you form G is equal to the cyclic subgroup of the set of permutations generated by sigma, all right, then the if you look at sigma is decomposed into beta 1, beta 2, beta, say T of sigma. So this is the disjoint cycle factorization of sigma. Remember, we more or less proved such a thing exists earlier in the course, remember? Then if you look at that, right, if I equals to I naught is moved by beta sub j, which let's suppose is I naught, I1, I sub r minus 1, then it's pretty easy to see that the orbit of I is just going to be equal to what? These are disjoint cycles, right? Every cycle except for beta j doesn't do anything to I. And as you act on by sigma, you're just cycling through, if you will, the j cycle, right? So you just hit whatever's in here. So the orbits are exactly the numbers which appear in the disjoint cycles. So to find the orbits of this group, you just basically take the disjoint cycles and just, those are the orbits, just rewriting them as sets. And then, of course, anything which doesn't appear is fixed by sigma, and those give you little singleton orbits. And that's it. Let's see here. Schnikes. Let's see here. Corollary to the orbit stabilizer theorem. If X is an element of a group, finite group, then the number of conjugates, of X is the index of its centralizer. In other words, the G C X is equal to the order of this set, Gx, G inverse, such that G is in G. How do you get that? Well, how about that example? I think we could use that example, right? So you think about the group action of conjugation on the group itself, right? What are the orbits? They're the conjugacy classes, right? So this says that the orbit of the conjugacy, the orbit which is the conjugacy class, the size of the orbit, is equal to the number of left cosets of the centralizer. The centralizer being the stabilizer of X under conjugacy action. So this is just the orbit stabilizer theorem applied to the conjugacy action is what this is. Now, let me just show you what this means for us, and then I'll shut up for today. If you look at S4, right? What are the number of conjugacy classes? So if you look at the cycle type, I'll draw a representative example. There's one here. And this is your number of this type, this kind. How many cycles of length 1? There's just one, right? How many transpositions in S4? I'll put you out of your misery. There are 6. How many 3 cycles? Distinct 3 cycles in S4? There are 8. There's no 1 over here. How many things like this? 1, 2, 3, 4. 4 cycles, there are 6 of these guys. But there's another kind of 4 cycle. 1, 2, 3, 4. This is 3. These different cycle types, like all of the different cycles in a particular cycle type, they're conjugate to one another. All right? This conjugacy class is an orbit under the conjugate action of the permutation group on itself. And the point of that early calculation I had you guys do, when you did conjugation by sigma, if you look at it, what happened when you conjugated by sigma was you got back the same numbers again, but in a different order. So it says that if you take a cycle with like 1, 3, 7, and you conjugate it, what you're going to get back is 1, 3, and 7 again. They could be in a different order, but it's still 1, 3, 7. So they're members of the same, they produce the same orbit with respect to this idea, and they're in the same conjugacy class. The thing that's striking about this, guys, 1 plus 6 plus 8 plus 6 plus 3 is what? 24, right? Because there's 24 permutations on 4 symbols. So the different cycle types, they have to add up to 24 because there's 24 permutations in this kind. And anyway, I'll shut up here. I was sad because I was mourning the death of Cauchy's theorem for today. Cauchy's theorem is it's amazing, and you'll see next time.